Imagine a future where computers learn, think, and adapt nearly as fast as humans do, but powered by light instead of electricity. This is not science fiction. It's the cutting edge of photonic computing, a technology that could revolutionize how we handle vast amounts of data, faster, and with much less energy. But here's where it gets controversial. The major stumbling block preventing photonic computing from reaching its full potential lies in a process called electro-optic, EO conversion. It's like bottlenecking an expressway with a narrow toll booth. No matter how fast the photons travel, if converting electronic data into optical signals is slow and power-hungry, the entire system suffers. Let's start from the beginning. Artificial intelligence, AI, is evolving at a breakneck speed, driving demand for immense computational power that traditional electronic systems struggle to meet due to their physical and energy limitations. This struggle sparks the search for novel computing architectures that move beyond conventional electronics. One of the most promising frontiers is photonic computing, where information is processed using photons, particles of light, instead of electrons. Photons are naturally equipped with high bandwidth and can carry multiple streams of information simultaneously by taking advantage of their frequency and polarization properties. This inherent parallelism allows photonic systems to perform calculations at speeds and efficiencies that traditional electronic circuits can only dream of. Thanks to breakthroughs in integrated photonics, the creation of complex optical circuits on tiny chips, photonic computing has evolved from a theoretical concept to a practical contender. Various demonstrations have utilized arrays of optical interferometers, free space optical setups, and silicon photonic circuits equipped with elements like attenuators and photodetectors. There are even systems using vertical cavity surface-emitting lasers, VCSELs, and microcombs for frequency multiplexing. These diverse implementations highlight how flexible and capable photonic computing can be. Yet, the Achilles heel remains: converting data from the electronic domain, where most information is stored, to the optical domain, where photons do the processing. This EO conversion is typically slow and consumes a lot of energy. Existing methods to perform EO conversion, such as variable optical attenuators or high-speed EO modulators, can handle data rates from kilohertz to gigahertz. However, these methods often suffer from high energy consumption on the electronic side and optical signal losses. Other tools like static amplitude masks or spatial light modulators save energy but refresh too slowly to be practical for many applications. Hence, the EO conversion bottleneck is the most significant challenge to deploying photonic computing widely. To tackle this problem, we focus on harnessing the electro-optic effect in thin-film lithium niobate, TFLN photonic circuits. TFLN is a material known for its exceptional EO properties, which means it can change light's properties rapidly and with very low energy. Recent advances in this platform have led to impressive components like high-speed modulators, frequency shifters, and optical comb generators, all of which play a role in efficient photonic circuits. Tight confinement of light and electronic signals in these tiny structures, combined with very low optical losses, allow us to integrate many EO devices on a single chip without significant degradation in performance. Our breakthrough is the development of a photonic accelerator on TFLN that can perform matrix vector multiplication, MVM, with high speed and low power consumption. This operation is a cornerstone of neural networks and AI algorithms. Unlike other demonstrations, our system integrates a hybrid laser source and fast photovoltaic detectors directly onto the chip, enabling seamless EO data conversion and computation within a compact footprint. Here's how it works. Electronic data originating from a computer is transferred into the photonic accelerator through modulating the amplitude of a continuous laser beam. This modulated light is then split across multiple spatial channels, Think of it as distributing information along parallel highways. Each channel applies its own weighting through another set of modulators, which perform element-wise multiplication of vectors encoded in the optical amplitudes. Finally, the light intensities are detected and converted back into electrical signals, completing the computation with remarkable speed and energy efficiency. Plugging this concept into practice required sophisticated photonic integration. Our chip uses 2 computing cores, each with 16 channels, though one modulator was unfortunately lost during fabrication. The optical waveguides are meticulously etched for smooth walls, minimizing signal loss to just 0.28 dB per centimeter, crucial for keeping energy consumption low across the circuit. The microwave transmission lines powering the modulators are carefully designed for optimal signal delivery, involving multi-layer gold films and nickel-chromium resistors that balance high-power handling with compactness. Each 1 centimeter modulator is capable of functioning beyond 40 gigahertz, demonstrating both wide bandwidth and high modulation depth. Testing our system showed impressive results. We successfully performed vector multiplications at a blistering rate of 43.8 billion operations per second, GOPS, per channel, while consuming just 0.576 picojoules per operation, a figure that challenges many electronic accelerators. Accuracy per channel stayed high, with only minor deviations attributed to passive optical components, and the system proved robust across varying optical power inputs. To demonstrate real-world capabilities, we applied our photonic accelerator to machine learning tasks. First, a binary classification problem based on an exclusive OR rule was solved with 93.8% accuracy, closely matching software results. Taking a step further, we classified handwritten digits from the NMIS dataset using a 2-layer neural network structure implemented partly in photonics and partly electronically, achieving an 88% accuracy compared to 92% from purely electronic calculations. The system showed outstanding stability, running identical tasks over 20 continuous hours with minimal error fluctuation. Perhaps most excitingly, we tackled complex image recognition on the CFAR-10 dataset. By pre-processing images through convolutional layers, which could also hypothetically be mapped onto photonic hardware, our TFLN circuit efficiently processed input vectors through fully connected neural network layers, correctly classifying images from all 10 categories, including trucks, cats, birds, and horses. Such multi-layer, multi-class classification tasks are often seen as benchmarks for advanced AI. Pushing boundaries even further, we integrated hybrid elements onto the TFLN chip itself, a distributed feedback DFB laser, and an ultra-fast photodiode to eliminate bulky off-chip components. These integrated devices maintain high performance with low threshold currents and dark currents, vital for reducing system-wide power consumption. Operating at 10.33 gigabytes in this integrated setup, the system demonstrates this progress is a massive step towards scalable, efficient photonic computing. The fabrication process benefits from wafer-scale technology, enabling batch production of compact computing cores, and paving the way for massive spatial multiplexing beyond just temporal encoding. Future enhancements, like lowering modulation voltage requirements, increasing bandwidth to 100 gigahertz, and reducing optical propagation losses to almost negligible levels, have already been demonstrated in separate TFLN devices, and can be incorporated to push performance even further. One potentially controversial point to consider. While our